I want to begin with a very simple question. A question that sounds on the surface almost childlike, but which, when you follow it seriously, leads you into the deepest and most unsettling territory that physics has to offer. The question is this: where is everybody? That phrase, "where is everybody," is attributed to the physicist Enrico Fermi, who reportedly asked it over lunch one afternoon in 1950. He was gesturing at an apparent contradiction. The universe is immensely old. It is immensely large. The conditions that gave rise to life on Earth do not seem, on the face of it, to be extraordinarily rare. And yet silence. No signals. No visitors. No messages scratched into the cosmic microwave background. Nothing. The sky is empty of intelligence, and it has been so for as long as we have been listening. This is the Fermi paradox, and it is not a paradox that has been resolved. In fact, I would argue that the more deeply you understand the physics of this universe, truly understand it, the more that silence begins to make a certain terrible sense. Now, I should say at the outset that I am not in the business of making theological claims. I am a mathematician and a physicist, and what I want to do is follow the numbers where they lead. And the numbers, I'm afraid, lead somewhere rather lonely. Let us start with the universe itself, with its beginning. When we talk about the Big Bang, there is a tendency to think of it as an explosion, a sort of cosmic firework, an initial burst of energy and matter from which everything else followed rather naturally. But this picture is deeply misleading. What the Big Bang actually was, from the point of view of thermodynamics, was something of almost incomprehensible specialness, and I mean that in a precise mathematical sense. The second law of thermodynamics tells us that entropy, the measure of disorder in a system, always increases over time. Always. You cannot unmix cream from coffee. You cannot reassemble a shattered glass. The universe moves, relentlessly and irreversibly, from states of order towards states of disorder. This is one of the most fundamental and well-established laws in all of physics, and it raises a question that most physicists sweep rather quickly under the rug, which is, if entropy always increases, why was it so low to begin with? The early universe was not merely ordered, it was extraordinarily, implausibly, almost miraculously ordered. The matter was distributed with breathtaking uniformity. The gravitational degrees of freedom, and this is the crucial point, were frozen in a state of vanishingly small entropy. When I tried to put a number on this, the result genuinely surprised even me. The probability of the universe beginning in the particular low entropy state that it did, chosen at random from all the possible states it could have occupied, is approximately 1 in 10 to the power of 10 to the power of 123. I want you to sit with that number for a moment, because it is not like other large numbers you may have encountered. It is not merely large, it is a number so staggeringly, obscenely improbable that the entire history of human thought has not produced adequate language to describe it. If you wrote a 0 on every proton and neutron in the observable universe, you would not come close to writing down all the zeros in that number. Now, why does this matter for the question of extraterrestrial life? It matters because of what that ordered beginning makes possible. That extraordinarily low entropy state at the Big Bang is what gives us the second law of thermodynamics operating as it does. It is what allows there to be stars, which are fundamentally engines that exploit the entropy gradient between the hot nuclear furnace in their cores and the cold darkness of space. It is what allows planets to form, and chemistry to operate, and eventually biological structures of extraordinary complexity to arise and sustain themselves. Life, as we understand it, is a process of local entropy reduction, sustained by feeding off a larger entropic gradient provided by a star. Without that original, impossibly special low entropy beginning, none of this would exist. You would have a universe of black holes and thermal equilibrium, and absolutely nothing else. So the question becomes, was that specialness of the initial state something that follows inevitably from the laws of physics, or was it an additional constraint, a boundary condition imposed somehow on top of the laws? And here I want to be very honest with you. We don't know. Current physics does not explain why the universe began in a low entropy state. Inflation, the idea that the very early universe underwent a period of exponential expansion, is often presented as solving this problem, but I have been arguing for many years that it does not. Inflation itself requires extraordinarily special initial conditions to get started. It doesn't dissolve the fine-tuning problem, it pushes it back one step. Now, some of my colleagues would invoke the anthropic principle at this stage. The argument goes roughly as follows. We observe a low-entropy universe, because only in a low-entropy universe is there someone around to do the observing. If the initial conditions had been different, we simply wouldn't be here to notice. And in a certain narrow logical sense, this is true. But it is deeply unsatisfying as a scientific explanation, and it leads to a rather disturbing consequence when you take it seriously. Here is the problem. If we are invoking the idea that our universe has the initial conditions it does simply because those conditions permitted us to exist, then we should ask, what is the minimum level of order required to produce observers? The answer is much, much less than what we actually have. To produce a single planet with intelligent life, you don't need a vast, elegant, mathematically precise cosmos stretching for 46 billion light-years in every direction. You need far, far less. The excess order in our universe, the fact that it is orders of magnitude more special than it would need to be, merely to produce one instance of intelligent life, is something that the anthropic argument cannot explain. The universe is not just ordered enough for us, it is absurdly, extravagantly more ordered than it would need to be, and that is, from a physicist's standpoint, deeply puzzling. Let me now bring this to bear directly on the question of whether we are alone. I mentioned the Fermi paradox. I want to explore it not from the perspective of sociology or speculation about alien civilizations' motivations, but from the perspective of physics and probability. When we look at our solar system, we find one planet. This one that developed intelligent life. We don't find it on Mars, we don't find it on Europa, we find it precisely here, under conditions that required not just the right chemistry, but an enormous succession of precise circumstances. The Earth sits in the habitable zone of a stable star. It has a large moon that stabilizes its axial tilt, making climate relatively stable over geological time. It has a magnetic field that protects it from solar radiation. It had the right delivery of water and organic molecules. It had mass extinction events that cleared evolutionary space at the right moments. Each of these things is not guaranteed. Each is a contingency. Now, in a universe of hundreds of billions of galaxies, each containing hundreds of billions of stars, shouldn't the sheer volume of opportunity overwhelm these contingencies? This is the naive, probabilistic argument for extraterrestrial intelligence, and it is not obviously wrong, but I think it underestimates something crucial. It underestimates the depth of the improbability involved in getting from simple chemistry to genuinely complex, information processing, technologically capable life. The gap between the chemistry of amino acids and the emergence of something like a mind is not a small gap. It is a gulf of almost unimaginable depth, and we have at present absolutely no physical theory that tells us how to bridge it. There is also a temporal argument that strikes me as important. For another civilization to be communicating with us, or traveling toward us, or leaving any detectable trace, it would need to have developed a significant technological capability. That means it would need to be at least roughly comparable to us in its development, perhaps somewhat ahead, perhaps somewhat behind. But the universe is 13.8 billion years old, and the timescale over which a civilization might remain detectable is tiny in comparison. We have been producing radio signals for less than 200 years. Our civilization may persist for another 1,000, or 10,000, or 1,000,000 years, but even 1,000,000 years is less than 1/10,000th of the age of the universe. For two civilizations to overlap in time and be close enough in space to communicate is not just a matter of both existing somewhere, it is a matter of an extraordinary temporal coincidence on top of an extraordinary spatial coincidence on top of all the biological and chemical improbabilities already mentioned. Now I want to turn to something that I think is even more fundamental, and it connects to ideas I have been developing for some time in my work on conformal cyclic cosmology. When we think about intelligence, when we think about what it means for a mind to understand the universe, we are, I believe, talking about something that is genuinely difficult to account for within a purely mechanistic framework. I have argued at length in The Emperor's New Mind and in Shadows of the Mind that mathematical understanding, the kind of understanding that allows a human mathematician to grasp the truth of Gödel's theorem, or to follow a proof, or to see why a mathematical structure must be as it is not the kind of thing that any computational algorithm, however complex, can fully replicate. There is something in genuine understanding that goes beyond computation. Now I hold this view cautiously. It is contested, and I acknowledge that. But the point I want to make here is that whatever it is that gives rise to conscious understanding, mathematical intelligence, whatever physical or quasi-physical process underlies it, seems to be extraordinarily rare in the universe. We have exactly one example of it that we can examine. We don't know if it requires quantum gravitational effects at the level of microtubules within neurons, as I have speculated. We don't know if it emerged inevitably from the chemistry of carbon, or if it required some very specific evolutionary pathway that happened to be taken only here. What we do know is that the universe has been around for nearly 14 billion years, has given rise to somewhere in the region of 10 to the power of 24 stars, and has, as far as we can tell, produced exactly one kind of creature that can sit down and ask why. I think that is remarkable. and I think the silence of the cosmos is not a failure of our listening equipment. I think it may be telling us something true and important about the nature of mind, the nature of matter, and the extraordinary, I might even say singular, improbability of our being here at all. There is one more thing I want to address, and it comes from my work on conformal cyclic cosmology, the idea that our universe is one in a potentially infinite sequence of aeons, each beginning with what we would call a Big Bang, and ending in a vast cold dark expansion, reaching something like a heat death. In this picture, each aeon is separated from the next, not by destruction, in any ordinary sense, but by a conformal rescaling, a mathematical transformation that identifies the remote future of one aeon with the beginning of the next. The physics is subtle, and I won't go through it in detail here. But one question I have been asked is whether intelligence or information could persist across such a boundary. Could a sufficiently advanced civilization from a previous aeon have encoded something in the geometry of space-time that we might be able to read? It is a beautiful question. I find it genuinely exciting. But I have to be honest, the possibility, while logically conceivable, seems to me extremely unlikely. The conformal boundary between aeons is not a gentle crossing. The degrees of freedom available to transmit structured information across it are vanishingly small. If there were civilizations in previous aeons that reached extraordinary levels of development, and I have no particular reason to think there were, the most we might expect to find are faint statistical anomalies in the cosmic microwave background. Hawking points, perhaps, the faint thermal echoes of evaporating black holes from the previous aeon. Not messages, not signals, just thermodynamic whispers from a universe that ended long before ours began. So where does this leave us? Let me try to draw the threads together. The universe began in a state of entropy so low that no probability theory we possess can make it seem anything other than extraordinarily special. That specialness is what makes the second law of thermodynamics possible, and therefore what makes stars, chemistry, biology, and minds possible. The physics does not explain why it was so special. We don't have a satisfying account of why the initial conditions were what they were. Then on top of that extraordinarily rare cosmic initial condition, we have the further improbability of a planet with the right properties, orbiting the right kind of star, at the right distance, with the right geological and chemical history, producing the right kind of self-replicating molecules, under evolutionary pressures that happen to select for intelligence. And then on top of that, we have whatever it is, and we genuinely don't know what it is, that gives rise to conscious experience and mathematical understanding, rather than merely complex information processing. The universe is, by the best physics we have, a place in which all of this happening even once is so improbable as to beggar the imagination. The idea that it has happened billions of times, that the galaxy is teeming with intelligence waiting to be found, that the silence is merely a matter of distance or technology. I confess I find this harder and harder to maintain as a serious scientific position, the more carefully I look at the numbers. I want to be clear, I am not saying it is impossible. Absence of evidence is not evidence of absence, as the saying goes, and the universe is genuinely vast. But I am saying that the physics, taken seriously, on its own terms, without wishful thinking, points in a sobering direction. It points toward a cosmos of almost incomprehensible scale and age, governed by mathematical laws of extraordinary elegance and precision, which has, in all probability, produced minds in only one place that we know of. Here, this fragile water-covered rock, circling an unremarkable star in the outer arm of one galaxy among hundreds of billions. That is either the most humbling conclusion imaginable, or depending on how you look at it, the most remarkable thing in the universe. I find myself, as I have grown older, increasingly inclined toward the latter view, not because I find comfort in it, I'm not sure comfort is quite the right word, but because the mathematics seems to demand it, and mathematics, in my experience, is rarely wrong about this sort of thing. We may well be, in the most rigorous physical sense that I know how to state it, utterly and completely alone, and perhaps the most honest response to that, the most scientific response I would even say, is not despair but wonder. Thank you.